8.1, we're going to look at simplifying radical expressions. This is a short unit, just 2 sections. And in part A, we're going to look at simplifying square roots. The first part right here, these numeric square roots are a review from quite a while ago when we simplified for the quadratic formula. I already know that the square root of 64 simplifies as 8, because that one comes out exactly. And I already know that the square root of 32 can be broken down because it's a perfect square, namely 16, that divides into it. So I can simplify this as the square root of 16 times the square root of 2. Then we can do the square root of 16 and get 4 times the square root of 2. All right. Now, those are problems with radicals that we have done before. What we're going to be seeing in this section is how do I deal with variables underneath radicals. That's going to be the new part. All right, so the inverse relationship between roots and powers. If I have the nth root of a equals b, that can also be written as, there are a couple ways. One of them is a to the 1 over n equals b, that's in fractional format. Or if I flip the n onto the other side, a equals b to the n. So in either case, the radical format or the exponent format, this would be the inverse statement. N is called the index of, and the symbol is called the radical sign. The notation square root of x without writing a little 2 is shorthand for having a little 2 in there. And a, the part inside the radical sign, is called the radicand. So I'm going to rewrite each of the following in a reduced radical and a simplified exponential. So we will be using our exponentials as well. So as a reduced radical, because we're more familiar maybe with the exponentials from our previous work, let's go ahead and fill in this column first. If I look at x to the 12 under the square root, that's the same thing as the 1/2 power. And I know that those two powers will multiply. A power on a power multiplies from way, way back. And so that would be x to the 6th. Okay? So the reduced radical form of this one is also x to the 6th. There's no radical left in that one. Okay? And the same thing here. This came out evenly is what we're saying, to x to the 6th. The same thing here. This will be 3x plus 4 to the 20th to the 1/2 power. Once again, those powers, using an exponent rule, multiply. 20 times 1/2 is 10. So that gives us 3x plus 4 to the 10th. That is also how the radical simplifies. 3x plus 4 to the 10th. So you can see that what's happening here is we are dividing by the index. So another way to think about this is, that is x to the 12 divided by 2, x to the 6th. This is 3x plus 4 to the 20, write my division that way, divided by 2, giving me the 3x plus 4 to the 10th. I'm multiplying by 1 over the index, or just dividing by the index. Two ways of thinking about the same thing. In the second objective, we're going to look at some properties for radicals. We already have these properties from a long time ago for exponent form, and since radicals are exponents, just fractional powers, we can do the same thing for radical form. So if I have the square root of a times b, that's the square root of a times the square root of b. Those don't have to be square roots, they could be nth roots. So we throw a little n in each of those roots as well. Nth root of a, nth root of b. We saw this when we were looking at the numeric form. Now we see it again as we're going to be looking with variables. Same thing up here. If I have the nth root of a over b, that's the same thing as writing the nth root of a divided by the nth root of b. Keep in mind that I can separate products and quotients, but we cannot separate sums and differences. The distributive property needs to be used, and they just can't be simplified in exponential form, they can't be simplified in radical form. Alright, let's look at the next page. Simplify or explain why it cannot be simplified. Okay, this This is a product of 25 and x to the 6th, so I can do those separately. And think about the square root of 25 and the square root of x to the 6th. The square root of 25 is 5, and the square root of x to the 6th will be x to the 3rd. Remember that that power comes up and basically divides by 2, which is the index, right? So this is a divide by 2. 6 divided by 2 is 3. So that would be the simplified version, 5x to the 3rd. Now here, these are both perfect squares where they're a sum, so I cannot simplify this. I cannot simplify two pieces separately if they're in a sum. So it's nothing I can do with that. I can simplify a product, and I can simplify a quotient though. So look at the next one. Okay, so this is the same thing as the square root of 16 times the square root of a to the 16th over the square root of b to the 10th. I know the square root of 16 is 4, and for each of my powers, since the index is 2, we'll be dividing them by 2. So that's going to be a to the 8th over b to the 5th. For a to the 8th over b to the 5th. All right, in our third objective, we're going to be simplifying some that don't come out perfectly. I think the first two do, and we'll see what we have later on. I'm going to pull out all perfect nth powers, whether they're numbers or variables. So z squared, that one comes out perfectly. I know that if I divide by 2, which is the index, I end up with z to the 2 divided by 2, which is 1, so I end up with z. In 49t to the 4th, I end up with the square root of 49 is 7, and t to the 4 divided by 2, which is 2, so I have 7t squared. Now 12, not a perfect square, so I'm going to start breaking things down. And that's the square root of 4 times the square root of 3a. The square root of 4 I can do, so I'll get 2 times the square root of 3a. The leftover pieces get to stay in the same radical, so 3 and a are in the same radical. I was only able to do the 2. All right. So in this one I was able to do some of the number, but not the variable. There weren't enough a's to divide out by 2. In the next one, I'll be able to do some of the number and some variable as well. So let's think about our 54. We can break it into 9 and 6, so square root of 9, square root of 6. And then we're going to keep all of our x's together because we are able to divide that 6 by 3, by 2. I get 3. Divide by 2, which is the index. So here we get to do the two pieces that are perfect squares. And we'll write the results of those first. Square root of 9 is 3. The square root of x to the 6 is x to the 3rd. We'll put the square root of 6, a piece we were unable to evaluate, last. In the next one, we're going to look at something that I can do part of the letters, not all. C to the 11th. I can't divide that by 2 evenly, so I need to separate it. Remember that c to the 11th is just c times c times c times c times c times c. So when I break it down, I can pull off one of those c's and say this is the square root of c to the 10th times the square root of one more c. I'm going down to the next even number. So I'm taking 1 away, because that 1 made it odd. I'm going down to the next even number. Then I can divide it by the index, which is 2. So 10 divided by 2 is 5. C to the 5th comes out, and the square root of c will be left inside. We took our 11, which was odd, pulled just one of them off because the next lower number was even, divisible by 2. Now that radical has been simplified. Let's try it again in the next one. This 4x minus 1 is a group. Unlike part B above, where they were separate, you can't do a separate sum or difference, but you can do a single group to a power. So I can separate those. Separate that into 4x minus 1 to the 12th, and then one more 4x minus 1 to make 13. I can divide by the index, which is 2, to separate this into the quantity 4x minus 1 to the 6th power times the square root of the 1 remaining 4x minus 1. You need to keep the parentheses on the outside there because that whole thing is to the 6th power. I was able to drop them on the inside of the radical because a power 1 doesn't need to be written. All right, and our last two. Here we get to play with both our number and our variable. 45 is divisible by 9. Not sure if you were able to hear my clock. Sorry if you were. It just went off. So 45 is divisible by 9. And so I can separate that into square root of 9 and square root of 5. And then for the y's, I can separate that into y to the 20th and y to the 1st. So we're going to be able to do the square root of 9. We're going to be able to do the square root of y to the 20th. And we'll leave the other two pieces in their radicals. Put them back together, actually. Square root of 9 is 3. Divide by the index, which is 2, gives us y to the 10th. And then we'll put the square root of 5 and y back together. They don't need to stay separate. The leftovers can go back into a single radical. All right, and the last piece, we have an 8. So we're going to separate that into square root of 4, square root of 2. Looking for those perfect squares that go into 8. So 4 goes into 8. Then a. Okay, 15 is odd, so I'll go into 14 and 1. A to the 14th and a. B. 3 is odd, so we'll separate that into b squared and b. We're going to be able to evaluate the perfect squares of 4. A to the 14th, b to the 2nd. Those will come out front. The square root of 4 is 2. The square root of a to the 14th, a to the 7th. The square root of b squared, b. The leftovers in the same radical, so I have 2ab.